Well, hello friends. Welcome back to the program. Today we are going to continue working on the kernel heap allocator in Serenity OS. So in the last video we got started with cleaning up some of the old technical debt, and specifically we made the allocator not have to call itself in order to grow the kernel heap. So today, we are going to dig into some other parts of the allocator. But before I start, I do want to recommend Linus's YouTube channel. So Linus is one of the Serenity OS hackers that you probably already know from my monthly update videos. And he recently started making YouTube videos of himself programming and working on Serenity OS. So I definitely recommend that you check out Linus's channel as well and give him your support by subscribing and checking out the videos. So I'll leave a link to his channel in the video description. Anyway, so today about kmalloc, what we're going to look at is slab allocation. So we have this thing in the kernel called the slab allocator, which is, it's essentially a separate heap allocator for objects where we know the size at compile time. So we can make a specialized allocator that only knows how to give out allocations of that specific size. And because of that, the metadata becomes very simple, right? It's just a simple free list of available slabs. But the way that the slab allocator works is quite messy. So let me show you how it works actually. So when we initialize this thing on startup, what we do is here, slab alloc init. We create a total of 5 different sub allocators for these sizes. So 16, 32, 64, 128, and 256 bytes. And then we give them this much memory each. What we do when we init one of these things is that we actually turn around and call kmalloc eternal, which is another kernel heap allocator. So we make an eternal allocation to store the entire slab budget into. And then this thing sort of sits on top of that allocation for the duration of its lifetime. And as you can imagine, it's certainly possible that you would allocate more than 512 kilobytes worth of 64-byte allocations. And what ends up happening if you try to do that is that we will run out of slabs, and we don't have a free slab, so we just fall back to regular kmalloc. So this thing is convoluted, I would say, and not particularly, like, it doesn't scale obviously because it only has a limited amount of memory available for the slabs, and there's no way to grow that. And it also requires that you use a macro when you declare a class. So we have this thing called make slab allocated, and as you can see, it's only used by 4 different types. So this thing is barely used at all. So the custody object, for example, gets slab allocated. This thing will insert a custom operator new and operator delete that just calls slab alloc and slab dealloc. So I think a much better thing here would be if this kind of behavior, so fast allocation for specific small sizes, if that would just be built into kmalloc, right? And then we wouldn't need the slab allocator to be a special thing on its own. You wouldn't need to use this macro in classes and so on, and all of this could just go away. Everybody could get the benefit of slab allocation automatically when they just call kmalloc. And one of the things that makes slab allocation possible, or at least convenient, is that slab dealloc always takes the allocation size. So when we want to find which slab allocator a given slab came from, whenever you're freeing one of these slabs, you also provide the size, which then allows us to locate the allocator in which it belongs. And if you imagine that it looked more like a traditional kfree API, like this, right? Then how would we know which slab allocator to free this pointer from? Well, we would have to, I don't know, walk through all of them and check, are you within the bounds of this allocator or something like that? So that's not optimal, obviously, but we are really good about always providing the allocation size when we free stuff in the kernel. So we have this thing called kfree sized, which is used almost everywhere. I think there might be some places that use naked kfree. Yeah, there are a handful of places. But I'd like to imagine that we can just get rid of all of these and then use kfree sized everywhere, which would allow us to do the slab allocator, fast path everywhere, and so on. But we have to start somewhere. So let's think about how we would approach this. And we're probably not going to do the final, most beautiful design in the world today, but we are going to try and get something that allows us to get rid of the old slab allocator at least, and then have something we can iterate on to improve further. So I think if we start at kmalloc, let's say. So you are calling kmalloc with a size, and currently the workhorse of that is kmalloc global allocate. So I think right here is where we could do something for smaller sizes. So we could have, for example, slab heap, and we could iterate through a set of slab heaps, and if one of them can satisfy the request, then we allocate from there. So something like this, slab heap dot size, or slab size, slab heap dot allocate, right? Something like that. And deallocation would work similarly for now. Let's say that we just check, I guess, oh, right, we don't have the size coming in here. Yeah, so that becomes our first issue. Like, we have to make sure that deallocate gets the size. So let's just take care of that first before we do anything else. Okay, so deallocate, and then if we open up the little problem view here, we can see that right here is where we're calling deallocate. So we'll pass in a size. All right. And we don't have a size here, but we do have one in kfree sized. So maybe the first order of business is to just get rid of kfree and replace it with kfree sized everywhere. So let's see if we can just do that in one go. So verify size is greater than 0. Okay. And then before we do anything else, let's just try to get prune kfree, essentially. Kfree sized, sorry. Okay. So kfree has to go away. All right, and then now we got to find everybody who calls this and get rid of them. So this demangling stuff is not used in the kernel anymore, I hope. Right, it's only used in user space, so that we can live without. Kfree directory kernel. Okay, so it's actually just this call right here and this call right here that we need to do something about. And the slab allocator one, let's see. So I guess yeah, so we're not getting rid of Slab allocator just yet, so we just have to keep it working. So we do have a kfree in the Slab allocator. And it has a corresponding kmalloc. That's this one right here. So that's the fallback path. You didn't have any slabs available. We returned a regular kmalloc pointer. So we will simply turn around and do the same thing for kfree, where we pass along the slab size. That's what we pass to kmalloc. So that's all taken care of. And then we have another guy right here. So kfree aligned. Okay, that's a little trickier. So the way that aligned allocations work in the kernel is there's a special API called kmalloc aligned, where you ask for a size, but you also specify an alignment. And this allows you to request, I want 16 bytes, but I want it to be aligned on a page boundary or like a 128 byte boundary or whatever. And what we do for that is we just pad the allocation, as you can see here, with the alignment and also some space for metadata. And then we shift the return pointer so that it ends up on the alignment boundary. And we store some metadata some metadata that allows us to locate the real allocation address. And that's what kfree align then sort of excavates here and passes along to kfree. So it's one pointer before the initial address that we return. So I think we can just, we can just store 2 pointers, or like we can store a size t right before that, I think. And let's put that into a thing like this. Something like that. Total size, and then we have we'll store the full size of the padded allocation right there. Padded allocation size, or real allocation size. Yeah. And then here, when we are trying to free an align pointer, we just have to dig that thing out. So we are going to call kfree sized with, let's see, I guess we just dereference that as a size t pointer. So putter subscript -2. Okay. That seems reasonable. Wait, this makes me remember that there are 2 variants of kmalloc aligned. There's kmalloc aligned and there's kmalloc aligned CXX, which is used by operators that take a std align val. Oh, I see. So I think the difference here is that the alignment here is a regular parameter, whereas with the original kmalloc align, the alignment is a template parameter. Making that a template feels a little bit like like a little bit overkill. Maybe like it's not the biggest deal if we have to compute that's tiny a bit of arithmetic at runtime. I can't imagine that that would matter, because it's not like we're doing a lot of these at all. So in fact, let's run with that intuition and let's get rid of this guy in favor of kmalloc aligned CXX or whatever. So let's see, let's do that. And where is that? Oh, this is a static local in kmalloc CPP. Well, let's promote this to a a global API, and we can put that right here. We'll get rid of this thing, and then we do the, oh, now I got rid of that mutation, but we can recreate that here. So real allocation size. And you know what? We should be good boys and use a checked so that we can fail on overflow, because that would be the responsible thing to do. And I'm gonna go ahead and add those two together here, because I am reasonably confident that these two together will not overflow the 32-bit range. But yeah, so then we'll call that value on it here, which will, this will panic the kernel if we have an integer overflow. If you somehow manage to trick this thing somehow into an integer overflow, will at least panic. Okay, and then let's do that thing again where we write the real allocation size. Okay. Dot value, sure. And get rid of the weird CXX suffix. Okay. Make aligned allocated. Oh, I have to. To change the way that it's used, of course. All right. So this feels okay. I think the slab allocator change we can actually do by itself. So let's add that one and make a commit. Maybe a few more dot slashes. Use kfree sized in slab allocator. Okay, and then does this actually, I'm curious to see if this compiles or if we have some hidden use of kfree somewhere that I'm not thinking of. Oh, wait, shit. We actually do compile demangle into this thing? I thought for sure we were not building demangling into the kernel. That's so weird. Wait, where do we use demangle? An elf image, sure. So this is not used if def kernel, and demangle. Right, so both of these are, both calls are not built on kernel. So I think we can actually do something like this, if in def kernel. Yeah, let's just like build that out on the kernel build. So because it's not used anyway, and why have this weird call? It's interesting that we've had this dependency all along on barbar cxa demangle. Anyway, it's all good now. We're just gonna don't include act demangle in kernel builds. This was not used anywhere in the kernel anyway. Okay. And without that, it does build. Does it run? That would be interesting. I mean, why wouldn't it run? We are just stashing an additional size t with aligned allocations. Come on now. Okay, we're good. And we can run JavaScript. Yeah, if you can run JavaScript, then probably you're doing something right. So JavaScript test suite passes. Cool. So let's commit then. Let's commit this stuff and say, wait, shoot. Now I'm committing too many things at the same time. Let's start over. So I wanted to do this. I wanted to only the kmalloc align changes. So I don't want to get rid of kfree just yet. So not this change, but yes, this change. Let's see, kernel consolidate kmalloc aligned and use kfree sized within. This patch does two things. Combines kmalloc aligned alignment size and kmalloc aligned. Let's just say like this: kmalloc aligned and kmalloc aligned. CXX. Templatizing a single, templatizing the alignment parameter doesn't seem like a valuable enough optimization to justify having two identical implementations. Almost identical implementations. And it also stores the real allocation size of an aligned allocation along with the other alignment metadata and uses it in order to call, kfree sized instead of kfree. Cool. Now we can get rid of kfree. Remove kfree, leaving only kfree sized. That is kick-ass. Let's comment a little bit more actually about that. There are no more users of the old school, of the C style kfree API in the kernel. So let's get rid of it and enjoy the new world of always, the new world where we always know how much memory we are freeing. That is a nice new world. All right, so backtracking to kmalloc. What did I want to do now that I have this? I wanted to pass it along to deallocate. Right, so deallocate can now take a size. So kfree sized can pass along that size to deallocate. Yes. And let's see. So far we have nothing to do with it, but let's add that in a separate commit so that it just sits there. Actually, we can improve this error message down here. Kfree sized. Bogus pointer passed to kfree sized, and then we'll do this. Kernel pass allocation size to log bogus log purported size of bogus kfree sized requests. Yeah. Okie dokie. And now that we have all the information, we can try to make a slab heap. So what were we saying? We were saying for auto slab heap in slab heaps. If slab heap, if the size is less than or equal to slab heap dot slab size, return slab heap dot allocate. All right. And likewise, when we deallocate, we try to deallocate the pointer. Yeah, that's how we're going to do this. Okay, and then we have to have a, let's see, what's this going to be? The slab heap collection here. I guess we have to come up with what is a slab heap. So let's make it something like kmalloc slab heap. And I'm saying to you right now that slab heap is a word for today. So what do we put in this thing? I guess it needs to have a slab size. Slab size. Sure. And then we also need to have a bunch of blocks. So that would be, let's see, we want a kmalloc slab block. And we'll allocate these things and keep them in some kind of a list. So here we'll put an intrusive list node to kmalloc slab block. Sure. Yeah, these things will eventually need to become classes and stuff, but since we're still prototyping, let's just keep it simple. So then this guy, the slab heap, will have intrusive lists. So one intrusive list of kmalloc slab block list node that we call usable blocks. And then we'll have one for full blocks as well. And whenever this will allow us to skip over completely full blocks when we're trying to find a block to allocate from. And then we can move slab blocks between these two lists as their fullness status changes. So let's see. So we create these slab heaps, and I guess let's just make a bunch of them. So right now, we have our sub heaps right here. And let's also make slab heaps. But for the slab heaps, we're going to just have a static set of them. So that would be something more like kmalloc slab heap, slab heaps. How about 5 of them? So we'll have a 16, 32, 64, 128, and 256 byte slab heaps. Yeah, that seems reasonable. Maybe we'll add a 512 one for good luck. Yeah, that seems okay. And then those will then be constructed at startup. That's fine. And we need an API to query the slab size. Maybe we'll make this a class right away, actually, because, you know, why not? We already put M prefixes on things, so. Size T, slab size, const, return, slab size. All right. And then this guy needs an allocate API. that can just do that, right? And it also needs a deallocate API. And how do we allocate? Well, we look through our list of usable blocks. So if m usable blocks is empty, we have to allocate a new block. Fix me, allocate new block. We'll do that in a moment, but then here we have a new block. And then what we do is auto putter is m usable blocks, or no, we'll do this first. Block, here we go. Block take, or no, we'll have an allocate API on the block as well. And then if block is full, so if there are no more allocations available after we take one, then we will move it to the full blocks list. So like that. And then we return the pointer. And then the beauty of intrusive list is that if you have two intrusive lists like this, like usable and full, if you append something to one while it is in the other, it will just move from one to the other. So you can only be in one intrusive list at a time, and it's okay to append to another list. It's just that then you disappear from the first one. So that's sort of baked into that, the behavior of that class. So let's give Slab block an API called allocate. And it also needs a deallocate API. And it needs an isFull API. And I think those are the APIs that we were using, right? Yeah. Deallocate pointer. So we need to pass in, wait, why do we need to pass anything? Deallocate. Oh, it needs to take an argument. Okay, so let's do the simplest form of deallocation first. So we can just, I'm just thinking, how are we going to allocate these blocks? So what we can do is we can do a trick that we already use in malloc and libjs for the garbage collector, where we make an aligned allocation, and then you will be able to find the containing block of any allocation, any slab, by doing arithmetic on its pointer. So I guess we can do that here too. Seems very reasonable at this stage. So let's just do that. By having, let's see, how big are the blocks going to be? Let's say block size will be 64 kilobytes. Okay. And then we can also have a block mask to aid in pointer arithmetic. So block mask will be block size -1, and then we neg the bits so that we get a mask that we can use to remove all of the bits, or the bottom bits from any slab pointer, and give us the address of the slab block. Yes, and then we'll do a class here as well right away, just because. All right. So this guy is going to need a free list. So let's see how we build a free list. Let's just do what we normally do and just make a simple singly linked list structure like this. Something like that. And free list entry, m free list, null putter. Okay, and then deallocating and allocating. Allocating becomes if This just becomes return, exchange your current free list with free list next. Because we should only call here if we actually have, we should only ever call allocate on a slab block if it is in the usable blocks list, right? So free list should be non-null. And when we deallocate, we say mfree list or putter, free list entry is free list entry putter. Free list entry next is the old free list pointer, and then we set the free list to free list entry. I guess that's fine. Okay, and then fullness. Fullness means that your free list is null. That means that you cannot allocate anymore from this guy. So that is only used when we decide if we're going to transition somebody from usable to full. Okay. That seems all right. And then we also need to initialize that free list when we construct one of these things. So let's just do that in an unoptimized way. So let's see, slab count is, where are the slabs actually? They're going to be here at the end of the block. So U8, let's call it data. GNU aligned. Let's hardcore align these things, or I guess maybe 16 is enough. Okay. Okay. And then we, that's the block size minus size of the kmalloc slab block class, right? So the size of this thing will be 0, but we will get the full size leading up to this thing. So we subtract that from the total block size, and then we can divide that by the slab size, which is a parameter. Okay. And then we make a free list entry to data at which subscript? Well, that's slab, or no, I times slab size. Something like that. And I guess that's an alignment warning that we're getting. I have to take address of. Yeah. Okay. Yeah, so it's a little bit messy, but I think maybe it's going to be okay. So free list entry next is mfree list. Yeah, this is not the optimal way, of course, to build a free list. I think the optimal way would be to start out in a bump allocator mode and then transition to a free list once you've bump allocated your way from the start of the block to the end of the block. That's an optimization we do elsewhere, but for now, let's just do it this way because it's kind of easier to write out. And then there's lots of room for optimizations and stuff. So that seems reasonable. We have our free list. And when you want to deallocate, then we need to locate the specific slab block for the pointer. So block is going to be flat pointer, and kmalloc slab block mask. So we end off the bottom bits, and then we will cast this concoction to a kmalloc slab block. And yeah, we're not doing like a lot of verification and checking that everything is on the up and up. That's something that we need to expand on eventually, of course. But right now, we just want to build something that that can work. So block deallocate putter, let's say. And I guess here we can do a little bit of a check. So we can verify that putter is greater than or equal to m data, or amp m data, I guess. And we can, let's see, we can verify that putter is less than U8 this plus block size. Yeah, so we can verify that it's within the bounds of the mdata byte array at the end of the block. That seems like a small little thing we can check. Okay. Oh, right. And then when you deallocate, I guess, then a block needs to never be in the, it should never be in the full list after you deallocate. So we can do something like block was full, block is full. So were you full before? If the block was full, then m usable blocks append block. So we move it to the usable blocks list at that point. Very cool. All right. So how do we allocate a new block? Well, we will simply make a allocation slot, which we will kmalloc aligned. We'll ask for the kmalloc slab block size aligned by kmalloc slab block size. Boom. Yes. And if that fails, that means that, well, for now we'll just panic while growing a slab heap. And then we can say which slab heap we're growing, so m slab size. But of course, the real fix me dare to return null putter. Once we get better at handling null putter or like allocation failures, once the rest of the kernel can actually react to these properly, then we can start returning them. For now, it would just cause chaos. So we'll leave that as a fix me. Okay, so now we have a slot, and we simply need to instantiate a new kmalloc slab block in that slot, passing in our slab size. Okay. And then usable blocks append. Or, well, I guess append or prepend doesn't matter because the list is empty. Yeah, I was thinking, should we append or prepend? But in this case, it doesn't matter. All right, will this work? What am I forgetting? So I guess it compiles at least. So the idea now is that when you call into the kmalloc allocator, we will walk a list of slab heaps. And if we find one where the size is adequate for the requested allocation size, we will simply get a slab from that slab heap. And when you deallocate, again, if the size is serviceable by one of our slab heap allocators, we will deallocate into that slab heap. And deallocation will mask the provided pointer so that we find the containing block, and then deallocate into that block, which will put the newly deallocated thing at the head of the free list, replacing whatever was there. Okay. Okay, all right. Let's see if it runs. Ah, not today. All right, all right, all right. I guess we must have screwed something up. So I wonder what. Let's see. So what was the first thing that went wrong? Oh, wait. Assertion failed, alignment less than 4096. Wait, where am I trying to go? 407. That seems like a totally arbitrary restriction. So I'm just gonna, like, why wouldn't we allow you to specify whatever alignment you want? I have no idea why that restriction was there. I mean, I guess we never used any larger alignment, but now we're trying to get these 64K blocks. And does it run? Ooh, it runs. Haha. Man, that was so close to first try. Just that one little check there, which we summarily got rid of, and look at him go. It just runs. That is just spiffy. So let's see that we're actually using the slab allocator. So allocate, let's see. Let's just add some debug statement here. So let's print something colorful. How about in a beautiful green? Slab, and then maybe the size and pointer, or pointer and size. Yeah, that seems okay. So putter and slab size, sure. We can even say plus 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 slab, and then minus 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 slab when we deallocate. Ooh, and let's put it in red when we deallocate. Ooh, yeah. All right. I just want to see that we get a bunch of green and red here, the Christmassy colors. Verify that we are indeed lab. Okay, I forgot to put an M here. That was a bit silly. I mean, it clearly does work, but we're just not seeing the pluses and minuses. So I don't know if they're actually getting freed, but it's really cool seeing that that we can service these using the slab allocator. So the big benefit of the slab allocator, we didn't even talk about that, is that, as you can see, like allocating, like effectively the allocation, once you've found which slab heap to allocate from, it's just a matter of taking the first usable block and then doing a simple pointer exchange. So like allocation is ultra simple and fast because it just does so little work. And likewise, the allocation is not a lot of work either. It's just a matter of doing a little bit of arithmetic to find the block and then shoving it into the free list of that block. So substantially less work than what the standard kmalloc does, which is to like find first fit or find best fit in a gigantic bitmap of memory chunks. So very, very nice. So let's see. So it evidently does a lot of allocations, and do note that the old slab allocator is still around, of course. We didn't actually change that. So all of these situations here are things that were previously serviced by standard kmalloc, now being serviced by the automatic slab allocator. Very, very sweet. lot of good stuff. So I think I'm pretty happy with this one for a first cut. There are definitely improvements we can make. I think maybe we're going to make that bottom alignment requirement removal separately. Kernel remove arbitrary alignment requirement from kmalloc aligned. It was not, we were not allowing alignments greater than page size for some reason. Okay, now we can commit our first version of kmalloc slab heap. Give kmalloc use slab allocation for small kmalloc requests automatically. Or should we use one of my favorite words, automagically? I think we will. So this patch adds kmalloc slab adds slab allocators to let's say generic slab allocators to kmalloc. The initial in this initial version, the slab sizes are 1632, 64, 128, 256, and 512 bytes. Slab heaps are backed by 64 kilobyte blocks, and use similar with free lists, block aligned blocks with free lists, similar to what we do in libc malloc and libjs heap. Yeah, let's just start with that. The goal here today is not to build the fastest or the strongest, most secure or whatever slab allocator, but rather just build something automatic that goes into kmalloc so that we can get rid of this custom slab allocator. And then my overarching goal is to unify allocation in the kernel so that we bring all the different allocators together, and then we have a single place to improve allocation. Instead of having many bad allocators, we can have one decent one and then improve that. I think that will be a nice strategy for us, at least in the near future. Longer term, there are certainly situations where you want a custom allocator because you have some additional constraint, or you have some especially valuable knowledge about your allocation patterns that you could use a custom allocator to exploit. But for the generic kmalloc allocator, I would rather have a one decent allocator instead of a selection of semi-decent allocators or sub-decent allocators. So let's see if we can just get rid of make slab allocated. So what happens if we just yeet that macro from all of the classes that are using it? What will happen? I'm downright curious if this will work, or if these things somehow depend on that mechanism somehow. I don't know. There's sometimes unexpected surprises when you're working on kernel stuff. Like stuff that works accidentally because side effects of something else. So we'll see. But I can't really imagine, I don't know what would make this not work, because we've been using this as an optimization only, the slab allocator. And as far as I can see, the optimization should be equivalent now. And well, moment of truth is coming up anyway. We'll see if if it builds, which it seems to. And then we'll see that it runs. So the slab allocator as implemented, by the way, does have a little bit of a sad flaw that we need to improve upon, but not at this very moment. But so what we do when we allocate these, right, is that we do a kmalloc aligned, and as we already saw kmalloc aligned earlier today, it does do a padding trick in order to guarantee that we can service the alignment request within the allocation. So we pad the size requested by the alignment and then shift the pointer. So there is a bit of like you end up wasting memory here, because we're passing in 64K size and 64K alignment. So you're effectively allocating 128K in order to get a 64K block. So that is not ideal. That is something that we can certainly improve by making our own allocation mechanism for these. It shouldn't be terribly difficult, since we already have the stuff we did in the last video for regular generic heaps, where we just manually handle the virtual memory address space allocation and the page table setup, all of that jazz. Anyway, it built and it came up and it runs JavaScript, which is just kick-ass. So let's see, does it run the regular test suite? Oh, it certainly seems to. This is really cool. I love that it's so perfectly possible to replace something as low level as the kernel heap allocator without too much pain, right? It's not terribly dangerous, and if you can just like replace it bit by bit and try to work towards something better. So let's see. Kernel remove all uses of make slab allocated. These objects that were previously slab allocated are allocated via slab alloc, slab dealloc. Now go through kmalloc, kfree sized instead. Yes. I should add a fix me about the spill that we get from the alignment. Where's that thing? Right here. Fix me. Kmalloc aligned. This came out. This allocation wastes block size bytes due to the implementation of kmalloc aligned. We don't handle this manually. Instead, handle this with a custom VM plus page allocator instead of using kmalloc align. Yeah, but that will be an exercise for our future selves. I think, yes. Kernel add fix me about allocation waste in kmalloc slab heap. Sure. Okay. What are you upset about? Oh, recursive call. Oh, that's fine. So let's get rid of slab allocator then. This will be nice. So git rm kernel heap slab allocator go bye-bye. That is just very, very tasteful. Slab allocator. Good. Bye. To you. Slab allocator. Haha. Slab alloc init. No need to call you anymore. Slab alloc stats. Not something we need to expose anymore through procfs. We don't need to check for the slab alloc scrub byte here. So let's see all of that stuff. Okay. Slab in kernel. Do we have any hits outside of kmalloc CPP? We do not. Okay, that is just very tasty. Although, speaking of scrub patterns, do we scrub these allocations? Where did we do the scrubbing for? Okay, so we need to scrub actually, because the old slab allocator would scrub, and our generic allocator currently scrubs, so we don't want to have unscrubbed slabs. Scrubbing is just something that's what we call clearing the memory that you get from kmalloc or that you give to kfree. So we are going to make sure we scrub those guys as well. But first thing, let's just make sure that it still builds with the slab allocator removed. Yeah, it seems like it's going to. Kernel, remove old slab allocator. This is no longer useful since kmalloc does automatic slab allocation without you having, without any of the sad limitations of the old slab allocator. Well, we don't have to say that they were sad. They were just limitations. Let's not shit on old code. Let's not. Right, so scrubbing. We need to scrub these things. So, I mean, scrubbing is a debugging and security mechanism. It's a debugging mechanism because it introduces a recognizable pattern in newly allocated and newly freed memory. So if you spot it in a crash dump, for example, you can see that, this memory looks like it was recently kmalloc'd or kfreed, right? Likewise, so that's why it's helpful for debugging. It's also helpful for security because if you had some kind of sensitive data in that allocation, then the next person who allocates the same piece of memory does not get to take part of whatever you had in there when it was your memory. So it is nice. The drawback, of course, is that it takes a little bit of CPU time to scrub out memory, but it's a hit that we will happily take. So let's see. We want to simply, we just want to memset, I guess. Actually, we want to do that. Do we want to do it here? Or I can do it at a higher level, because if we do it here, it kind of messes up the nice simplicity of this guy. So we can do it here instead. Right before we're going to return the pointer, we will simply scrub it first. So kmalloc scrub byte slab size. And when we deallocate, we will want to memset before we call the allocate, because the allocate will turn it into a free list entry. So we're just going to scrub it before we hand it back. So memset kfree scrub byte. Yes, there we go. And let's make sure that everything still works, of course. Scrub slab kmalloc slabs when allocated and deallocated. This matches the behavior of the generic subheaps and the old slab allocator implementation. Yes, I mean, that's seems like the right thing to do. So very, very cool. So after the last video, I did get some crashes that I didn't notice in the video when I ran when we ran on the CI, because the CI uses unaccelerated QEMU when doing the test. So let's go ahead and disable KVM. I always forget. Somebody added a way to do that recently. KVM support. Right. So I'm just gonna do that and do a run without KVM support and see that we're not getting some silly crash right away. As you can see, it runs way slower if you don't have KVM acceleration for QEMU. But that slowdown can often expose issues. It's especially good at exposing interesting race conditions that sort of disappear because you're going so fast with accelerated emulation. Or I guess it's not accelerated emulation so much as it is using hardware virtualization. But now we are just splitting hairs. So I think this is going to work out. This can take quite a while here, especially if you run the benchmarks. I think they take upwards of like half a minute or something sometimes. But yeah, I'm just gonna leave that running in the background and say that this will be the end of today's video. So if you made it this far, then I thank you for watching and for hanging out. I hope that you saw something interesting here. I'm certainly happy that we are finally doing something about this old comment here about how the kernel malloc and free are quick and dirty, and sort of starting to iterate towards improving this and allowing it to become hopefully a decent malloc and free implementation over time. We're not quite there yet, but today was another step. So now we got rid of the separate slab allocator, integrated it, automatic slabbing. Very, very cool. I don't know what we'll do next time. We'll figure something out. For now, thank you all for watching, and Merry Christmas to everybody. And I hope to see you next time. Bye.